Well, welcome everybody to the January 2022 meeting of the Mornington Peninsula Astronomical Society. Not held in person because of current COVID limitations. As you can see on the initial slide, a lot has happened since we last met, not least of which on the 15th of this month, so not that many days ago. We had a significant volcanic eruption in the island of Tonga off the east side of Australia, and shown in the top left-hand side of the screen are two images by NASA and NOAA satellites indicating the eruption in progress. And then over to the right, thanks to member Fred Prater pointing it out to us, is the log of atmospheric pressure as recorded by our small weather station located at the Briars on top of the observatory site. So as you can see, the little blip there is the pressure wave from the volcanic eruption finally passed over the Briars about 4 hours later, travelling at subsonic speeds. So all very exciting that can be picked up by just modest equipment. The big news story during the months of late December and January, of course, is the launch of the James Webb Space Telescope by NASA. This is a successor to the Hubble Space Telescope. Hubble operates mainly in the optical wavelength, so the light is pretty much what you see by eye. However, James Webb will operate in the infrared and far infrared sections of the spectrum. I believe it will also pick up some of the far red side optically as well. Now, James Webb is a telescope that has been on the drawing board since the 1980s, and indeed it's about a $10 billion investment by NASA into a single instrument, and at times was taking up about a quarter of their entire annual budget. So very, very substantial gamble. And hopefully everything goes okay and it gets to the special point in the heavens known as the L2 point, the second Lagrange point, where it will remain in orbit as long as its fuel remains, which is thought to be maybe 10 years. Currently we don't have any capabilities to go out that far and actually service it or provide extra fuel to it, but who knows, in 10 years time maybe a robotic craft can be designed to actually go out there and thereby extend the life of the spacecraft and its scientific mission. Now, it was launched just before midnight. It's about 11:20 here local time, Australian Eastern Daylight Saving Time, on Christmas night, so 25th of December. Launched from French Guiana, and the size of the mirror when it's finally deployed on the James Webb Telescope is about 9 times larger than the surface collecting area of Hubble, hence very much some aperture fever involved, and it will be able to get much fainter objects and look further back into the universe than any other spacecraft telescope has been able to do today. The couple of animations show the deployment sequence on the left of the James Webb Telescope, where it's been very neatly and ingeniously folded up to fit inside the rocket for launch, and then over a period of many days it will slowly be undone in a series of a few hundred steps, and any one of those steps, if they fail, could indeed sabotage or bring to an end the success of the mission. And it will begin those deployment unfurlings on the way to the Lagrange point L2. Now, L2 is a special point in Earth's orbit that's about 1.5 million kilometres away from Earth, and to give you a bit of perspective, the Moon itself is about 400,000 kilometres away from Earth, so we're looking at almost up to 4 times the Earth-Moon distance further away from the Earth than the actual Moon is. So we certainly don't have any manned technology that can go out that far, in contrast to the Hubble Space Telescope, which is merely in low Earth orbit, which is very low indeed, and certainly has been readily accessible in the past when the American Space Shuttle was operating. I'm not sure how well they'd get to it these days, though, with the shuttle out of service. On the right hand side is showing the orbit of the James Webb Telescope around the Earth and the Sun, and as you see, it doesn't go around in a simple circular or elliptical oval shaped orbit. It's very quite a substantial choreographic dance as it moves around the orbit. And the aim of that is to keep it in this special point in the sky, the L2 point, whereby the Earth and the Sun stay very close together in the sky, and that way the light from them and the heat from the Sun especially can be blocked by the heat shields on the spacecraft all the time, so they won't actually stray into the field of view unless something goes catastrophically wrong with the orientation of the spacecraft. So when it's fully deployed and at the Lagrange point and oriented, ready to take measurements, one side of the spacecraft on the sun-facing side will get up to 85 degrees Celsius, so not quite hot enough to boil water, but certainly very, very uncomfortable even for electronics here on Earth at that temperature. And on the other side of the spacecraft, where the instruments are pointing away from that direction, the temperature is minus 233 degrees Celsius, so very, very cold. Not certainly not at the coldness of deep space, which is getting on for a couple of degrees Kelvin only, which is down around minus 270 degrees Celsius. But nevertheless, the difference across the sunshade is an enormous number of degrees Celsius that that shading is protecting the spacecraft and its instruments from. Well, and on tonight, welcome everybody, especially to new members to the Society who we haven't had a chance yet to meet in person, and hopefully that will occur fairly soon. Now tonight I'll go through the events since we last met, and also those that are upcoming before our next meeting, and obviously they've been impacted somewhat by COVID. Then because the James Webb Space Telescope launched this month, in fact last month, and is well and truly on its way to the L2 point this month, I'll show a couple of features about it. The first one is a bit of a background on Dr. Amber Straughn, who's an excellent science communicator from the James Webb Space Telescope team, and she actually works for Goddard Space Flight Center. So a bit of a background on her, and then she'll give a lecture on a new era in astronomy, NASA's James Webb Space Telescope. This was a public lecture delivered in Canada a couple of years ago. However, the content of it is still as relevant today as it was then, going into the science objectives of the James Webb Space Telescope mission and what they hope to find from it. That of course hasn't changed over the last decade or so that NASA's been working on it. A couple of things actually in that talk is that some of the dates are a little bit outdated because the James Webb Space Telescope launch was delayed a couple of times, but if you ignore that, everything else is quite accurate, and she's an excellent science communicator as well, so probably one of the better talks about the James Webb that I've looked at myself. Following that, Mark Stevens will give Sky for the month of January, and after that we'll look a little bit more into the engineering behind the James Webb Telescope, given that it's an incredibly intricate dance of mechanical engineering to actually get it up and going on its way. At the time of recording this video, obviously it's launched and on its way, but next week I believe there'll be like a mid-course burn to try and insert it into the L2 trajectory to get it into orbit at the correct place. Now next month we'll look in some more depth at the Lagrange points. If you haven't heard about those before, the 5 Lagrange points, and there is some interesting videos on that one that I'll show you in next month's meeting. So we'll be looking at the engineering of the James Webb Space Telescope, and then because of the volcanic eruption in Tonga recently, we'll also look briefly at why volcanoes actually give you mushroom clouds, and this is an interesting demonstration by Professor James Jackson actually during a Royal Institution lecture in London a few years ago. And following that we'll close in the usual way, and this close today is an excellent video that NASA produces about once a year on the phases of the moon and the appearance and libration of the moon for the entire year, and they usually set that to some music as well, and you'll see that a little bit later. Always well worth a watch for that one. So recent events. Well, since we last met, 20th of November was due to be a telescope learning day, but of course because of COVID and the Omicron wave coming, that had to be cancelled. The next day was also going to be our Sunday fossil field trip to Mornington. Alas, that had to be cancelled after a long time in the planning as well. 24th of November we had a committee meeting on Zoom, and a number of things were talked about there. One was a grant that we've been successful in getting for audio-visual equipment for the Briars, a federal grant. We also looked at a sundial that was donated by Ian Sullivan a number of years ago, and where to put a stone cairn on the site to mount it permanently. And we also looked at a proposal that had been put forward by a Cranbourne brand to hold a Trivial Pursuit night actually up at the Briars with us, together with some music as well. And those who've been in the society a few years would be familiar with the one that we did with the band from Rosebud, although that was not a Trivial Pursuit night as such, so this one's a little bit different. 30th of November we were due to have Glenferrie Primary School visit the Briars. Alas, that couldn't go ahead due to COVID. On the 3rd of December we were going to have a public night, and again because of COVID we changed that to be a members only fully vaccinated night at the Briars, and Trevor Hand kindly stepped in to give his first M-rated talk for the Society. And this little bit risque talk at times was entitled The Space Race Behind Closed Doors, and there were plenty of members present, certainly up to our COVID density quotient limits for the space it was held in. 11th of December saw the Society come together for the Christmas dinner, the free Christmas catered dinner at the Briars, and that was, as usual, a great success, seeing many members that we don't often see during the year, and this tends to be a bit of a flagship event for a lot of members each year. 4th of January we held a committee meeting by Zoom, primarily to look at what we should do in response to the rising Omicron wave and the new restrictions coming into place for societies such as our own. And it was decided there in January and in February all the public nights would be called off, which was a bit of a shame because they were quite heavily booked, certainly up to our density limits allowable. In January, the first two were going to be given by Trevor Hand and Catherine McCoy, but alas, they were both called off. On the 13th of January, nevertheless, Trevor Hand managed to give a public talk at Carrum Downs Library, and he was fortunate enough to have 35 people present from the public there, so that all went very well. Right, coming up soon, 21st of January is due to be a public night at the Briars with a talk given by Manfred Berger, but alas, that has also been COVID cancelled. We are due to have a members working bee the next night, the Saturday night at the Briars, followed by a free barbecue at the Briars as well, and all members are welcome to participate there if they wish. Subject to the usual COVID restrictions that we currently have on site. On the 26th of January we're due to have our next committee meeting on Zoom. 28th of January was going to be another public night, as for 4th of February was going to be another public night, and those talks were going to be given by Guido Tack and Trevor Hand, and alas, both of those have been called off due to COVID. So probably, unless things change significantly in the next couple of weeks, the next public night is going to be the one for the first Friday of March. So the next time we're due to meet, and hopefully it's in person, but maybe it will be a recorded message such as this one, is due to be on Wednesday the 16th of February at 8 o'clock at the Briars, all being well.
For me as a scientist, I think the most exciting prospect of any telescope like this, any big, bold, ambitious telescope that we put into space, is this idea that there are questions we haven't even thought to ask yet, that we'll learn things about the universe that completely surprise us. I'm Amber Straughn, an astrophysicist at NASA's Goddard Space Flight Center. I'm on the NASA science team for JWST. My path to becoming an astronomer was maybe a little bit different than most. I grew up in the rural southern part of the United States. I was the first person in my family to go to college, and you know, when I was growing up I didn't really know any scientists, but I grew up under very dark skies, and those dark skies are what got me interested in astronomy as a young kid. In these deepest images with Hubble, we've been able to see back really far. We've been able to see some very distant galaxies, but what we haven't been able to see is the very first generation of galaxies that were born after the Big Bang. In order to do that, we need infrared light. We need a huge infrared telescope in space, and this is exactly what JWST is. In fact, JWST was designed with this idea in mind, to find the very first galaxies. Once we get the telescope to space, it has this intricate system of unfolding that it has to go through. That takes a couple weeks. Then it takes several more months for the telescope to get cold, to line up the mirrors, and then to turn the instruments on one at a time. So it'll be next summer, summer 2022, before we get the first images. We of course can't promise that we're going to find signs of life, but it's not an overstatement to say that this telescope is definitely our next huge step in our search for habitable planets in the Milky Way. There's so much riding on this telescope. It's the future of astrophysics, and we have to get it right.
So, on to the main talk for tonight by Dr. Amber Straughn from NASA, an astrophysicist there. Excellent science communicator. This is a public lecture that was given in Canada by the Perimeter Institute for Theoretical Physics, and includes some questions towards the end as well. Some of the dates are a little bit out of whack because the James Webb Space Telescope was delayed a number of times being launched, but nevertheless the content still remains accurate as to its background and scientific missions and what they hope to actually find from it.
Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to this, Perimeter's public lecture series presented by BMO Financial. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here this evening. Both those of you here in the theater audience and those of you watching online on Perimeter's website or on one of our many science communication colleagues' websites around the globe. The lecture itself will last approximately 1 hour and will be followed by a question and answer session. Dr. Damien Pope and a team of researchers are behind their keyboards, ready to engage in conversation for the online audience and answer questions throughout the lecture and after the lecture. If you want to participate in that conversation, use hashtag #PILive. And also, if you want to have a question sent in for our guest speaker, send that in early so that it can be vetted through the process and make it all the way to my phone in time for Q&A. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. Amber Straughn. Dr. Straughn is an astrophysicist at NASA's Goddard Spaceflight Center and is a member of the James Webb Space Telescope science team and the Associate Director of the Astrophysics Division at Goddard. She completed her PhD in physics at Arizona State University and has been involved in NASA programming since her undergrad, beginning with flying an experiment on NASA's microgravity KC-135 plane, also known as the Vomit Comet. She says she did not vomit. In addition to her research, Dr. Straughn's role with the James Webb Space Telescope science team involves, in addition to research, there's also lots of science communication. She is a highly sought after speaker who frequently gives talks at schools and astronomy clubs and museums and research societies. Dr. Straughn has appeared on the Discovery Channel, the Science Channel, PBS, Nova, National Geographic, BBC, the History Channel, Spike TV, and on Late Night with Jimmy Fallon and his Hubble Gotcha segment. Ladies and gentlemen, please join me in welcoming Dr. Amber Straughn and her talk, The New Era of Astronomy, NASA's James Webb Space Telescope.
Thank you so much. Thanks for that kind introduction. And thanks to the Perimeter Institute for being such a gracious host today. It's been so much fun talking to the researchers here and some of the students. And it really struck me today that we're so privileged as scientists working in communities like this to be able to work with creative, inspiring people who are doing things that they're so passionate about, things that they really love. And I feel like that's the same case for me at NASA. I have a job that I love, and I'm working with people who are doing really remarkable, incredible things. My passion for astronomy actually began a long time ago when I was a little kid. I grew up in rural Arkansas in the southern United States on a tiny farm. And as you might imagine, in a rural place like southern Arkansas, there's not a lot to do. But let me tell you something. The night sky was stunning. And so from the time I was a very young kid, I was interested in astronomy. I was looking up, and I was always asking my parents ridiculous questions that they couldn't quite answer. And I remember at one point, I asked my mom some out-of-this-world question. And she looked at me and she said, I don't know the answer to that question. This was the days before the internet. And she said, but you can figure it out. She said, you're going to have to find out the answers to those questions. And that really set me on my path to becoming an astronomer. And I've ended up here at NASA, which is a job that I truly love. And so I'm really excited tonight to tell you about this amazing project that I get to work on, and to tell you a little bit about the history of astronomy at NASA. And of course, we can't talk about astronomy without first talking about the iconic Hubble Space Telescope. Over the past 27 years almost, Hubble has completely revolutionized our understanding of the universe in fundamental ways. And one of the things I love most about astronomy is that the questions that we try to answer in astronomy are so much more than science questions. They're questions that get to the heart of what it means to be human beings. These are questions that humans have asked and sought the answers to since we've been able to ask questions at all as a species. And Hubble has done amazing things to help us try to start to answer these questions. So the Hubble Space Telescope has been able to tell us about the universe on a large range of scales, starting from our cosmic backyard of the solar system, and then stepping out further in our own Milky Way galaxy to star-forming regions, so relatively nearby in a cosmic sense. And then, of course, the Hubble Space Telescope has also taught us not only about star formation, but it's taught us about stellar deaths. And of course, this is the process by which elements are spread throughout the universe. The iron in your blood was literally formed inside of a star. And I think that fact is so amazing, and it connects us to the universe. So these stellar deaths are often very dramatic and beautiful. And of course, we've also learned from Hubble about other galaxies outside of our Milky Way. And we've learned that galaxies not only exist out there, but they also sometimes interact. So part of my own research deals with interacting galaxies, and this is an example, a beautiful example of the antenna galaxies that interact. And when galaxies undergo this cosmic dance of interaction, really fun things happen. They form stars at higher rates. We think their black holes probably merge, and that's one of the things that cause black holes to grow over time. So Hubble has provided us all of this information about our solar system, about our Milky Way galaxy, and about other galaxies outside of our Milky Way. And then it's also, of course, taught us a lot about the evolution of the universe as a whole. Now, if I had to pick one single image of all of Hubble's amazing images as my favorite, it would be this one. So this is the Hubble Ultra Deep Field. I was very lucky. This image came out when I was in graduate school, so I got to do a lot of my dissertation research on this data. But in the Hubble Ultra Deep Field, Hubble stared at one tiny piece of sky for about 11 days. So that's like looking at the universe through a straw. If you take a drinking straw and look up at the sky, it's this tiny little spot. You cover it up with your finger, your pinky. So in this tiny piece of sky, Hubble sees 10,000 galaxies. So every point of light there is a galaxy, a couple of stars scattered in there, but for the most part, they're all galaxies. And of course, these images are beautiful, but we also were able to learn remarkable amounts of things from these images. Just by looking at them, you can tell the galaxies come in a variety of shapes and sizes. You see in the foreground some common-looking galaxies, some spiral galaxies. But as we start to go deeper, we see that the universe changes as we look further back in time and further away in distance. And what we're able to do with these images and from spectra that we're able to take with these galaxies is learn about the chemical components of the stars. We're able to learn about these galaxies' black holes and how and if they change over time. And by looking at their distances, we're able to basically look back and track back into the early universe and figure out how, in a large scale, galaxies in the universe changed over time. And then, of course, at some point in these Hubble Deep Images, we come to the edge. We come to what we can no longer see. And so that's, of course, the topic of most of my talk tonight, is what we're going to do to get beyond that edge. So that's a very brief, condensed history of the amazing 27 almost years that Hubble has been in space. And the Hubble Space Telescope, I think, is, in addition to being this remarkable scientific machine, it's this thing that we humans have built that have given us answers about these big questions of the universe. I think it's really important, and it's really telling, that Hubble has become an element of pop culture. You see Hubble images on the sides of U-Haul trucks, and on album covers, and in movies, and on cartoons. Hubble images show up everywhere. You go anywhere in the industrialized world and you ask somebody to name a telescope, and they're probably going to say Hubble. And I think that really speaks to something deeper that these types of projects give to the world. I think that Hubble has become, again, not only an astronomer's tool, but it's become a resource for the world, a resource of inspiration, and it's really become something that we can be proud of as a species, of this thing that we've built that has taught us about the universe. And I don't really know exactly why. I don't know why people love Hubble so much. I'm glad that they do, but I'm not sure why. Of course, it's easy to be captivated and inspired by those beautiful images, but I'm not exactly sure why that is. I mean, they're beautiful, they're pretty, but why? You know, if you look at images of trees and of nature that we normally experience, it's easy to understand why we are captivated by those images. They're part of our experience, but nebulae aren't part of our daily experience. So it's really interesting. And again, I don't think I have the answers, but I think it might be connected to the fact that we, in some maybe subconscious level, some deep level, we know that we're connected to the universe. We know that when we look up at the universe, then in a sense, we're sort of looking back at ourselves. We're looking back at our origins of where we came from. And I think that concept is very beautiful, and it's universal. I think that the images that Hubble have given us, they transform, and they go beyond national boundaries and language boundaries. There's something that is very deep about the reasons that Hubble has become this worldwide icon. So in that sense, you know, this is a world treasure, I think, that we have. And so, of course, what's next? What's after Hubble? What could possibly follow up the amazing science that Hubble has given us, the amazing thing that it is? And that, of course, is the James Webb Space Telescope that we're building now. And I truly believe that this telescope will be a worthy successor to Hubble. I think that in a lot of ways we've pushed Hubble to its limits, as awesome as it is. And we're literally building this telescope to answer those next biggest questions in astronomy that Hubble just can't quite get to. So I want to tell you a little bit tonight about some of the science goals of this mission and some of the ways that this mission is different than Hubble. So the first big key difference between Hubble and Webb is simply the size. So overall, Hubble's about the size of a school bus. Webb is more the size of a tennis court. Its sunshield's about the size of a tennis court, and it stands several stories tall. Now, the size of a telescope's mirror is very important because it allows us to, number one, collect more light, and number two, allows us to see finer detail in those images. And so this will by far be the biggest telescope that we've ever sent into space, by far. So this is a model of the James Webb Space Telescope. This was at Goddard. Unfortunately, I'm not in that picture. Very sad. But a lot of my colleagues are, and this is, of course, just a subset of all the people that have worked on this telescope over the past 2 decades now. So this is a model, steel and plastic, not the real thing, obviously, wouldn't be sitting outside at Goddard. But you can sort of get a sense of the scale of the telescope here. Again, that sun shield, about the size of a tennis court, stands several stories tall, huge telescope. And again, the reason for that is because it's completely driven by the science questions. The second big difference between Hubble and Webb is the place in space that Webb will be. Hubble orbits the Earth about 350 miles up. This, of course, is not to scale. But Webb will orbit the Sun along with the Earth about 1 million miles out, about 1.5 million kilometers away from Earth. And it will follow the Earth in the orbit around the Sun. And so this is a point in space called the second Lagrange point, L2. It is a semi-stable point in the whole overall gravitational system of the Earth and the Sun. And it's a place where we can park spacecraft, and they sort of stay there, and they follow the Earth as it orbits the Sun. That way we can always have easy access to communications with the telescope. And so that's where we're putting the James Webb Space Telescope. And the reason we're putting it there is so that it can get very, very cold. And that leads to the third big difference between Hubble and Webb, which is the type of light that Webb will see. So Hubble is primarily an optical telescope. It sees the universe primarily in visible light that your eyes see. It has a little bit of near-infrared capability, but it's primarily an optical telescope. Webb will be an infrared telescope. It will see the universe in red light, red visible light, all the way out to mid-infrared. For those of you that speak in microns, it'll be 0.6 to 28.5 microns. So near-infrared all the way out to mid-infrared. And again, this is completely driven by the science questions that we want to answer with a telescope. So why infrared? Well, this is the iconic Pillars of Creation, the Eagle Nebula, the iconic image from Hubble in optical light. So here is a fade into UV light. This was taken a few years ago, and then it's going to fade to near infrared, and you'll see the reason that we need infrared. With infrared light, you're able to peer through the dust and see the stars inside being born. So that's one of the reasons we need infrared. People often ask me if the Hubble or if the Webb images will be beautiful like the Hubble images are. And I always point them to this. That's pretty beautiful, right? And that's a near infrared image from Hubble. And so absolutely we expect the Webb images to be stunningly beautiful. In addition to the amazing science we expect it to tell us. So those are the three big differences between Hubble and Webb: the size, the place in space, and the type of light that it will see. And so now I'm going to get to the science. What do we hope to learn with Webb? We have 4 main science themes, so 4 broad goals, things that we want to learn from Webb. So the first big goal is first light and reionization. So you remember that Hubble movie that zoomed through the Hubble Ultra Deep Field? We saw all those galaxies in the foreground, spiral galaxies, elliptical galaxies, and then you get to galaxies that have more strange shapes, and then you come to the edge. So when we look at these deep images from Hubble, the deepest image, or the deepest galaxies, the most distant galaxies that we see are these teeny tiny red dots. And I encourage you, if you haven't looked at this image in detail, to go download it in its full resolution and just scan around. You spend hours doing it. But the most distant galaxies we've been able to see with Hubble are these teeny tiny red dots, just a few pixels. So we don't know a lot about them, but what we do know is that they're not the first galaxies. From what we've been able to tell from these distant galaxies, they exhibit properties that tell us that they're not pristine. They're not the first galaxies. And so what we want to be able to do is push beyond that limit and use Webb to see the very first epoch of galaxies that were born after the Big Bang. So we're talking about looking back in time over 13.5 billion years to see that first epoch of galaxies. Now, this is not easy, of course. That's why it hasn't been done yet. We have our theorist friends that build these beautiful models of the early universe. This is a simulation of the early universe that tells us what we think we should see in the early universe. So we expect to be able to see these young galaxies, these infant galaxies that turned on after the sort of the cosmic dark ages. But again, we've never been able to have technology that's allowed us to see back that far. So we've gone on the theories, and now we want to be able to learn more about what's going on there. So just some sort of fundamental questions in this realm. So what are those first galaxies? What are they like? And when did they form? Do they have black holes? We expect they almost certainly do. How do they cluster? And this whole process about reionization. So early on in the universe was mostly filled with hydrogen gas. And if a photon comes along, if light comes along, hits hydrogen, it gets absorbed, it can't get through. And so what we want to do is find that first epoch of galaxies that were able to shine enough light to sort of blow bubbles in the surrounding neutral hydrogen so that we can see through to see those first galaxies. So how did that happen? We know it was probably sort of clumpy. It happened in different places. And we want to know what the history of that was up until what we think we've seen as the end, sort of the end of reionization. And so what caused it? Stars, black holes, how did all of that happen? So there's a lot of open questions about what those first sources were and how they affected the surrounding universe. So this is a timeline. Many of you have probably seen something similar of the history of the universe in a chart, right? And so we have the Big Bang over here, and then present day over here. And so again, with Hubble, we've been able to push back and start to see again what we think is sort of the end of reionization. But what we really want to do is to see those first things that started blowing out those bubbles and started to shine through to see the first galaxies after they emerged from the cosmic dark ages. It's one of the primary goals of JWST, and it was one of the drivers. It was one of the reasons that we started to build this telescope. So the second big science theme for Webb is galaxy assembly. And this is one that's very near and dear to my heart because this is my area of research. So we want to learn more about the process, the very basic process of how galaxies build up over time. So the Hubble sequence is the name we give to the nearby galaxies that are spiral galaxies, elliptical galaxies, balls of gas, or irregular galaxies. And that system holds pretty well, pretty true in the nearby universe. But once we start getting out more distant, it falls apart. Galaxies don't have the same structures. And so we want to learn about how that whole sequence formed in the present day universe. We want to know how the heavy elements formed. And we want to know about the interactions of the galaxies with their surroundings. So we think the interplay between galaxies and the gas that maybe feeds galaxies and feeds star formation. And then the galaxy's star formation and black holes, of course, give this outward winds. And so what is that interplay between galaxies and their surrounding environment? So all those questions we'll be able to learn more about those questions with Webb because we'll have this new telescope in this new wavelength regime in order to study these processes in detail. So it's the very fundamental question of how we go from those tiny red blobs in the Hubble Ultra Deep Field to these gigantic galaxies that we see in the present day universe that have these huge black holes at their centers. So we're able, of course, now with Hubble to study this in a statistical sense. I'm interested in galaxy mergers, and so this is a sequence, a snapshot of different galaxies that Hubble has taken. Of course, these processes take billions of years, so we have to study these things statistically. But I'm really interested in that process of how galaxies grow over time, and we think that this merging process is one of them. One of the really fun things about astronomy also is the interplay between theory and observations. So this video is showing steps between theory, simulations, which is what this part is, and then it will fade to an actual Hubble image. And so in this way, we're able to have theory inform observations, and then observations feed back into theory. But it's always a good thing when you're doing theoretical simulations and then the observations match up. And the great thing about Hubble is we have this wealth of knowledge, this wealth of data that allows us to go back and do these studies. So this third big theme for Webb is to see stars and protoplanetary systems being born. So back to the iconic Eagle Nebula here. So some of the detailed questions here that we want to answer. So these protostellar clouds that host the baby stars and the baby planet systems, how do those collapse? That's sort of the beginning point of forming stellar systems, solar systems, stellar systems. But there's a lot we don't know, and theory plays into this, but there's a lot we don't know about how they collapse down to begin with, and how the hydrogen at the centers of these clouds actually form their stars. I mean, stars are the building blocks of galaxies, and star formation is a very fundamental process in the universe, but there's still a lot about that process that we don't know. And we also want to know, same thing as with galaxies, how does the environment in which stars form, how does that environment affect the star formation, and then vice versa, how does the star formation affect the surrounding environment? So similar to galaxies, that whole environment interplay with the formation of these objects. And then getting down to thinking about the planets that are forming, these baby planets enshrouded in dust. How do those protoplanetary systems form? How do the dust grains come together and form the planets to begin with? And again, this goes back to the fact that these systems are enshrouded in dust. So this is another image of, this is the Carina Nebula, a Hubble optical image. And here is the perfect example of where stars are born, inside these big dust clouds. And so here, the image will fade here from optical to infrared. And again, you can see the utility of infrared in this area of study, because you're able to peer into that cloud, to see that newborn star through the dust, and to see its interactions even. In this particular case, you see the stars blowing jets, and so it's affecting its surrounding environment. So infrared is going to play a critical part in helping us answer questions about how early stars form and how protoplanetary systems form. And then this one. This is a fun one. So as I said, I study galaxy evolution. I'm really excited about what Webb will do in the area of galaxy evolution and finding those first galaxies. That's all going to be really, really cool stuff. This area is fairly far from my own personal area of research, but I think this is maybe the most exciting thing that Webb does, is to study exoplanets. And Webb will also have the capability to study planets within our own solar system. So everything from Mars on out, Webb will be able to study. And we have a very active planetary science team that is working on ways to use Webb to observe these objects in our solar system. So we fully plan to do that. So what do we want to learn? Of course, lots within our own solar system, but then in terms of exoplanets, what are the physical processes that lead to these planets? So sort of stepping from that last science theme of protoplanetary disks on further to when the actual planet formation happens. And then, of course, we want to be able to relate these exoplanet systems that we find elsewhere to our own solar system, and it will help us inform the studies of formation of our own solar system. And then, of course, habitable zones. How are they established? How do water and other elements get embedded in these habitable zones of exoplanet systems? So lots of really good questions there. Of course, we find exoplanets by transits. So the Kepler Space Telescope, of course, has been really instrumental in this in the last few years. And so this is a transit, and from just this very basic process of watching planets transit in front of their stars, we're able to learn fundamental things about the planets, like their relative masses and their distance and their orbital times. So there's fundamental things we can learn from watching planets transit their stars. And I think that one of the things that the Kepler Space Telescope has given us is really this knowledge that planets are common. So how many have seen this, the Kepler Ori? A few of you out there, okay. So this, to me, is one of the best astronomy visualizations there are. So this shows, and this is several years old, so this is certainly not all the Kepler planets, but this gives a visualization of the variety of exoplanet systems that Kepler had found to date. It's much bigger now. But what you see here is that just the variety of planets, right? Who would have dreamed that planets would have been not only this common, but this wild, right? There are planets of all different sizes orbiting their different sized stars and, multiple planet systems. I mean, it's remarkable to me that when I was a kid, the only planets we knew of were in our own solar system. And now we know that planets are absolutely everywhere. The Milky Way is literally teeming with planets. Statistically, almost every star in the Milky Way likely has at least one planet. I mean, go outside at night, point up at a star, probably has a planet around it. That's a fundamental paradigm shift between when I was a kid and now. And I think that is really incredible, that Kepler has given us this knowledge, and Kepler's a relatively small telescope. It stares at one part of the sky, does one thing, but it really has given us this immense knowledge of planet systems, and really just the fact that planets are common, something that we didn't know. So the next step, of course, is to do spectroscopy of these transiting planets. So we want to go from knowing that the planets are there to knowing what they're like. And this is going to be one of the big jobs of the James Webb Space Telescope. Now, so what do I mean when I say transit spectroscopy? What I mean is we want to watch these planets orbit in front of their stars, watch the starlight pass through the atmosphere, and then from that starlight filtering through the atmosphere, learn about the chemical components of that atmosphere. Sounds pretty simple, right? It's relatively simple, theoretically, but technically, it's really, really hard. And this image shows why. So this is the Venus transit from a few years ago. This is a real NASA image from one of our solar observatories. And so what you see here, which is the common theme, is that stars are bright, planets are tiny, and their atmospheres are minuscule. So separating out this signal from the bright stars and the tiny atmospheres is really technologically challenging, and we really couldn't do it in earnest really until now. So with Webb, we hope to be able to do that. We plan to do that. And every time I talk about exoplanet science with Webb, I always say, and I still say, that we have to get really, really, really lucky to find a system that might potentially have habitable planets. But sometimes nature delivers. And we had this awesome result last week. And of course, we don't know. We haven't studied these planets in detail yet. But how incredible that we have this planet system 40 light years away. This is our backyard. And it's the perfect system. It's a little tiny, faint star with a bunch of planets, 3 of which are solidly in the habitable zone. And so absolutely, this is going to be a great target for the Webb telescope. Who knows if the planets have atmospheres? A lot of planets, systems like this, planets close into their star, they can be tidally locked so that one side of the planet faces the star the whole time it's orbiting. We don't know. What we know is that those planets are there, and we definitely intend to look at them with Webb. So again, 7 planets orbiting this nearby star, just sort of hit the jackpot. I mean, what an incredible discovery. And so I can't imagine that my exoplanet scientist friends aren't drooling over this discovery and waiting for Webb. These planets were first discovered by the TRAPPIST telescopes in Lucia. And it's also a great story of how the ground-based telescopes, and this is Spitzer in this case, this result last week was from the small infrared Spitzer telescope. So a great story of how ground-based telescopes and space telescopes can play together to get these great results. But we really, really do need Webb in order to do spectroscopy for these faint, small, rocky planets. So that TRAPPIST system, a lot of fun. Really excited about that. So those are the science themes, the 4 broad themes with all these sub-questions and all this great stuff that we hope to be able to find out from the James Webb Space Telescope. So the great news, of course, is that we're building it. And not only are we building it, but we have built it. So almost all of the hardware for the James Webb Space Telescope, practically all of it, is finished, it's built. And a lot of the pieces have been built for years. This is a project that's been going on for decades, literally now. So the James Webb Space Telescope was first conceived shortly after Hubble was launched. So us astronomers, we always like more bigger telescopes. And so shortly after Hubble was launched, we started thinking about what might be next. And I say we, I was in elementary school, so I was a part of that conversation. But astronomers started thinking about that. And cool thing about the astronomy community and other science communities as well in the US, every 10 years, astronomers from around the world really get together and they say, what are our biggest astronomy questions today? And what do we need to build to answer them? And so those are the decadal surveys. And in the 2000 decadal survey, the answer to what do we need was the James Webb Space Telescope. So 2000 was really when it started getting going. There was development work, R&D that was done before that, but 2000 was when it got its seal of approval to start to move forward as a NASA mission. So that was a long time ago. It turns out building something like this is really hard. No surprise, right? So I want to take you through some of the steps of building it and some of the pieces. So of course, the iconic part of the telescope is that gigantic mirror with hexagons, these hexagonal segments. The mirrors themselves are made out of beryllium, and they have a really thin coating of gold. So the Spitzer telescope also has a beryllium mirror. It turns out that beryllium is a really good material to put out into deep space where it's very cold. It's very strong and lightweight, and it doesn't change shape much under drastic temperature changes. So obviously we have to build the telescope on Earth. In space, it's very cold, and so we need a material, all the materials need to be able to withstand those extreme temperature differences. So the mirrors were individually manufactured and tested. This is an image of the 3 of the 18 mirror segments coming into NASA Goddard. This all happened within the last couple years. So the mirrors were one of the technology elements on the telescope that really took a lot of lead time. Making these mirrors was really, really difficult. So in addition to the fact that just working with beryllium is difficult, the telescope itself has to be very, very precise in its prescription or its shape. And so if you imagine the Webb telescope mirror, so it's 6.5 meters across. So imagine stretching that whole mirror out to be the size of the United States, right, coast to coast. The biggest bump on that mirror would be a couple inches. So that's how smooth the mirror is. So machining these mirrors and coating and polishing them to that incredible precision is really difficult. So we started working on the mirrors really early on in the mission. And as of last year, a couple of years ago, we had them all completed, all individually tested. And then everything on this telescope has a practice round. So this is an image of our specially made robotic arm installing one of the test mirrors on a test structure. And this happened at Goddard back a few years ago. And then about this time last year, it's been almost exactly a year ago, we finished installing all of the 18 primary mirror segments onto the backplane. So this process took several months, of course, after all those individual tests of the individual mirrors. And of course, the process of placing them, and then they had to be individually mounted. And as you see, they're not gold here. So they all have these black caps on them to protect them while the mirrors were being installed. And so this whole process, again, was completed about a year ago. And then we took the caps off, and we have this beautiful gold mirror that was able to be seen at Goddard for a short period of time. It's now in testing, which I'll talk a little bit more about later. So in addition to the mirrors, of course, a really important part of the telescope are the instruments. And as a scientist, of course, the instruments are really important to me. This is where the data comes from. This is where the images and the spectra will come from. So we have 4 instruments on the Webb telescope. We have a near-infrared camera. We had a mid-infrared instrument. We have a near-infrared spectrograph, which has some really cool spectrograph technology. And then we have what's called the fine guidance sensor and the near-infrared imager and slitless spectrometer. That's a mouthful, but I wanted to say it because that is a Canadian instrument. The Canadian Space Agency is supplying the fine guidance sensor and the NIRISS instrument. So those two are packaged, those are functionally different, but packaged together as one, and they're provided by Canada. The fine guidance sensor is a mission-critical instrument on the telescope. So it essentially provides guidance and stability for the telescope when it's pointing at the objects it needs to observe. And then the near-infrared imager and slitless spectrometer will be able to take spectra of galaxies and of planets. It will be able to do actually really important exoplanet science. And so this particular instrument will be, I think, really instrumental to all 4 of the science themes that we have for Webb. So really excited about all these different instruments. All 4 of these instruments have now been integrated onto the core package together that goes on the back of the mirror, of the big gold mirror. And so here is a picture of part of that integration process. Now, all of these instruments, just like everything else on the telescope, were tested at an instrument level, at a subsystem level. And then when they're put together into these pieces, they are tested at a higher level. So all the instruments have been through 3 rounds of cryogenic testing. They've also been through vibration testing, acoustics testing, all of those sorts of things. So the instrument's really important. The sun shield. So we just finished completion of the last sun shield layer within the last year. So this is the sun shield is made out of a material called Kapton. It's a very thin plastic material with a highly reflective coating. It's 5 layers. And as you can see, there's a person up there for scale. It's really big. Everything about this telescope is really big. So the purpose of the 5 layers is so we can get very, very cold on the top. So in this sort of configuration, the mirrors and instruments would be up on top, and then the spacecraft buses down on the bottom. And so in that configuration, of course, the telescope would always point out away from the sun. So the sun shield is exactly what it sounds like. It shields the mirrors and instruments from the sun. And the reason for the layers is for thermal dissipation. Okay, so the temperature difference between the bottom layer and the top layer is about 600 degrees. So it turns out space is really good at that sort of thing. And so we're able to get this extreme temperature difference. Now, that poses a lot of issues too. Nothing about this telescope is easy. So the thermal properties of this telescope, of what goes on, even in the center section where you have the connection between the mirrors and the spacecraft underneath, lots of really interesting thermal physics problems that we have to solve in order to make this telescope work. So that's the sun shield. As I said, all 5 layers are completed. This is a video of some deployment testing. So Northrop Grumman is our prime contractor, and this is at their facility out in California. And so all the layers, of course, have been under cryogenic testing. This is a deployment test, obviously a manual deployment test. Lots of really, really extensive tests that go on for this telescope. As I mentioned, it's going to be far away, 4 times further away than the moon, 4 times further away than human beings have ever been. We cannot service this telescope like we serviced Hubble. So the telescope isn't serviceable. One of the reasons we have such a long, extensive test program, this telescope has to work once it gets into space. We can't go and fix it. And so that's why we have such an extensive test program here. The logistics for this telescope amaze me. So the engineering and the science obviously are amazing, but carting around pieces of a telescope that are this big, not an easy logistics problem. There's whole teams at NASA that work on logistics. So this is inside the white box is the big backplane structure when it arrived to NASA Goddard back a couple of years ago, and it's carted around on a C-53, that's the U.S. military's largest military aircraft. And landed at Andrews Air Force Base outside of DC. They shut down the Washington DC Beltway in the middle of the night and trucked the backplane in this truck along the Beltway at 5 miles an hour. It was really just interesting logistics for this for the whole telescope. And then, as I've mentioned, the test program for this telescope is extremely extensive. This is our cryo vacuum chamber at Goddard. So this is one of the tests that we did on the instrument package. And so again, we test the structure, and then we test the instruments integrated into the structure. And the instruments have all gone through 3 cryogenic tests. So that's testing the instruments down to about 10 degrees Kelvin, or 10 degrees above absolute zero, 10 Kelvin. So space is very cold, so we have to test all of our components in cryogenic temperatures. Now, our cryo vacuum chamber at Goddard was not able, it's a typical nitrogen cryo chamber, wasn't able to get that cold, so we had to use helium. So we installed a huge helium shroud inside the chamber to get us down to the cold temperatures that we needed to test these elements of the telescope. And so this is one of those tests. So that huge cryo chamber there, the top sort of is moved by a crane, lifts off, and then we've undergone these extensive tests of the instruments. The tests of the mirrors will happen, the individual tests have already happened, but coming up later in the program, we will send the whole telescope element, so the telescope and the instruments together, down to the Johnson Space Center in Houston to undergo full end-to-end optics cryogenic tests. It's a really critical test that's coming up later on this year. This happened just a couple of months ago, actually. So this is after some of the tests we had in the clean room at Goddard. We installed this huge tent over the telescope. So this, you can see now the mirrors, the 2 wings are folded back, the secondary mirror is folded up, and then the instruments are installed on the back of the mirror. So we installed this tent over the mirror because we had to move it out of the clean room to go to our other testing facilities outside. So everything is assembled inside the clean room. That's why everyone's in the protective bunny suits. But our vibration facility and acoustics test facility are in different parts of the building. They're just different facilities. And so we had to build all this test equipment in order to take the telescope, move the telescope from place to place. And so this is installation of that huge tent to go over the telescope here. So this is after the telescope and the tent has been moved out, and this was installation onto the vibration table. So the telescope is launching into space. It's launching on an Ariane 5 rocket, which is a European Space Agency rocket. And of course, the rocket ride is bumpy. So we have to shake the telescope to make sure that it will withstand the stresses that it experiences during launch. And so we had these custom vibration tables built for the telescope. Turns out there weren't any big enough in the world to accommodate this telescope, which is a common theme. And so we just completed these vibration tests just about a week ago. So this is a very recent occurrence in the life of the testing of this telescope. So this just happened very recently. Now, when you test things, occasionally you find problems. So in one of the first tests we had a little bit of a high load on one of the accelerometers. So we had to pause the test, make sure everything was okay, which it was, and then continue. But that's the exact reason we test. We have to make sure this telescope works once it gets into space, and so that's why we test on the ground. So this is an image from about 2 days ago. So this is like hot off the presses. So after we finished the vibration test, we moved the telescope into our acoustics testing chamber. So imagine enormous speakers that are going to blast the telescope with sound, and of course this is to test different vibrational frequencies of the telescope. So that test started just a few days ago, and it should be finishing up any day now. So lots of really critical environmental tests that are going on right now. So the telescope is big, that's a theme, right? It's too big to fit inside the rocket, fully deployed, so we have to fold it up, and it deploys once it's in space. So this is the deployment sequence of the telescope. So the first thing that pops out there is the solar panels. We'll use the solar panels for power, of course. The antenna pops out so we can talk to the telescope. And then as the sequence goes on, you will see that that 5-layer sun shield slowly unfolds. This whole process starts fairly soon after launch, and then it lasts about 14 days. So how many of you saw the Mars Curiosity 7 Minutes of Terror? It's a great video. Go check it out if you haven't seen it. So they had 7 minutes of terror. We have 2 weeks of. So again, one of the reasons we test this telescope so much is because this is hard. Okay, make no mistake about it. This is really, really difficult. This is coming up to the edge of impossible engineering. And so we're doing it at NASA, though, and that's one of the most amazing things about NASA is I think that we're able to take on these huge challenges and we're able to do them. And so this whole deployment process, again, takes about 2 weeks. And then after that all happens, we'll have a commissioning period where we take a few months to slowly phase up the mirrors to make sure the mirrors are all perfectly in shape. We'll turn on the instruments one by one and sort of bring those up to working order. And then we'll get the first science images sometime in the first 6 months. And then routine science operations will start about 6 months after launch. So you can expect to see the first images from the James Webb Space Telescope in sort of early 2019. What will they be? We don't know yet. We're undergoing a process now to figure out what those first observations will be. And in fact, we just had a huge science milestone this week. You know, a lot of our milestones we've been talking about lately in NASA have been engineering milestones. You know, we got through this test and we got this thing built and all these different engineering milestones have been met. We've met a scientific milestone recently this year as the call for proposals came out. So the call to ask scientists to write proposals to use this telescope came out, and the letters, the notice of intent that you're going to propose are due on Friday for the early release science. So it's real now. It's really real. It's really happening. We launch next year. That's soon. So October of next year is when late next year in 2018 is when we plan to launch. So the James Webb Space Telescope is the project I work on and the one that I'm probably most excited about, as you can probably tell. But at NASA, we have a whole huge suite of astrophysics missions that we are currently operating and that we will operate in the future. And so this is just a suite of the missions that we're involved with here. We have one, the NICER telescope is expected to launch in April. So that's going to launch on a SpaceX rocket, and it will be installed on the International Space Station. So we have lots of fun collaborations with the human spaceflight side of NASA, where we install spacecraft on the space station. So we have a whole fleet of astronomy observatories, astrophysics observatories at NASA. Of course, the ones that come along like Webb are the big ones, right? Most of these telescopes are relatively small telescopes that are focused on one specific thing. So the Kepler telescope, for example, was, its mission was to look at this one part of the sky, look at exoplanets. That's what it did. So most of NASA's astrophysics missions are like that. They have one sort of mission, one goal. And then you have the missions like Hubble and Webb that have these sort of multi-purpose missions. So they're built to explore a wide range of science questions. And I want to give a particular shout out to the next big mission after Webb, which is the WFIRST mission, the Wide Field Infrared Survey Telescope. So while Webb and Hubble are similar in that they look at sort of small pieces of the sky deeply, the WFIRST telescope is going to take images of a wide swath of the sky. And the WFIRST mission, if you haven't heard about it yet, go check it out, learn a little bit more about it because I'm running out of time. But its two primary science themes are, get this, so cool, exoplanet science and dark energy, two of the most fun things that we have. And so really excited about this mission, scheduled to launch in the mid-2020s. So excited about WFIRST, really excited about Webb. I invite you all to Go online, go to our website down here in the bottom left corner. Follow us on social media. Join us in this journey leading up to launch, marching to launch next year. And of course, then to the science that we'll reveal soon after that. This journey for me has been personally just really exciting to be a part of a team that's working on something that's so significant. This telescope has already shattered boundaries of space technology. But as a scientist, of course, I'm excited about the science that we'll do. And I've told you a little bit about the core science themes, the core science questions that we hope to answer with this telescope. And I'm sure we'll answer those. That's going to be a lot of fun trying to answer those. But for me as a scientist, I think the most exciting thing about these big, bold missions are the answers to the questions that we haven't even thought to ask yet. In the end, these missions that we build are all about the promise of discovery. They're about the promise of hundreds of billions of stars in these hundreds of billions of galaxies and untold surprises just waiting to be discovered. Thank you.
All right, well, let's open the floor to questions. Aiden, you're on.
So how do you protect the sensors before the sun shield has fully deployed?
That's a really good question. So the whole process of launch, of getting out there, is a process where we have to make sure that the rocket is sort of pointed in the right way, and then when the rocket cone falls off, we have to make sure that it's pointed in the right way. So it's all about making sure that the spacecraft is sort of pointed in the right direction. So if you notice when it starts off, the sun shield is sort of wrapped up around it. And so when it starts to unfold, to deploy, that's when we have to make sure that it's pointed in the right way, essentially. But that's a great question.
And what about the thermal aspects of it? Won't have a lot of problems relating to that?
Yeah, so the thermal aspects of the telescope have been one of the most challenging things. And even just the thermal properties from sort of the cold side under the sun shield to the hot side under the sun shield to the cold side on top. So the sun shield does a great job of protecting the mirrors and instruments. But there's that middle section, right, where the telescope basically connects to the spacecraft. And so figuring out the thermal properties of that section has been a real challenge. But we think we figured it out, and we expect that it's going to work like we want it to. Yeah.
Thank you, Aiden. All right, let's go online as others line up. Here's a question tied to the length of the mission. What is it like to work on a project that is decades in the making?
Yeah, so I've been involved personally in this project a little bit since I was a graduate student. My dissertation advisor in grad school is one of the 10 interdisciplinary scientists on the mission, and so I got interested and involved early on as a grad student. But you're absolutely right that these missions that span decades, people spend their entire careers on these missions sometimes. And so it's there's certainly people that besides me that have spent a lot longer than I have. And so I think it's great to be a part of that. Part of that is just the team that comes along with it, being a part of such a big team that's designing something like this and building something like this. But at the same time, we have to launch this thing to space. I mean, I already can sense some of the team at Goddard. The telescope itself will leave Goddard in April, sometime, next month. And there's a little bit of sadness, like our telescope is leaving. And then someday our telescope is launching to space. It's like sending a kid off to college or something. But so there's all parts of that. It's funny because it's an emotional thing. Like you pour your life into these missions, especially these missions that span decades. But it's a fun thing.
In theater.
Okay, so from my understanding of this, you're going to have to send an initiation signal to the satellite or the telescope to get it to unfold. Is there any redundancies you've built in so that you can, and how are you actually going to communicate to the satellite to make sure that it gets the signal?
So our the operations for the Webb telescope will be run out of the Space Telescope Science Institute in Baltimore, Maryland, same place where the Hubble is operated. So we use Ka band, normal sort of communication with the satellite, and absolutely there are redundancies built into the system. Not every move, you saw the deployment, not every movement has redundancy built in. It's just impossible. But many of them do. And the ones where we can place redundancies, we do. And so the process of communicating with the telescope, like you said, sort of happens one by one. And in fact, later this year, we start a full-up dress rehearsal of sorts of the launch and of the commissioning because it takes so long. And so, people are going to be, there's going to be 24-hour shifts and there are going to be people working. And so rehearsing all this and rehearsing what happens if something goes wrong, what do you do? So there's a whole rehearsal process for the whole process.
I'll take another one from the online list right now. The question is, was it just lucky that the TRAPPIST planets are on the same orbital plane as the solar system, or is that common? Lucky is an okay word to use, sure. So yeah, in a sense it is luck. It's statistics really, but you can say it's luck. So yeah, some of the systems that we see in the sky will just have the right inclination that we'll be able to see them transiting. Of course, a large fraction of the exoplanets won't have that. If they're face on, we can't see the transits. We can observe planets that are there in other ways, radial velocities, those sorts of things. But yeah, it was luck. I guess it was luck. You could say that the TRAPPIST system happened to be sort of edge on. Thank you. In theater.
So you mentioned that WFIRST is going to be used to study dark energy. How do you study dark energy?
What a great question. Yeah. So. Yeah, good question. So what it's going to do is it's basically going to survey many galaxies and go into the detailed distances of the galaxies, and from that just try to sort of hone in on the parameters of dark energy. So dark energy, of course, it's this. When astronomers don't know what something is, they call it dark, right? We got dark matter, we have dark energy, and it makes up most of the energy mass content of the universe. In fact, yeah, so everything I've talked about tonight, the billions of stars and planets and galaxies and all that makes up 5% of the universe. The rest, the 95%, we have no idea what it is. Dark energy, dark matter, don't know what it is. But the WFIRST telescope is going to do this really cool technique that you should go online and read about. Go on our website. It's called baryon acoustic oscillations. So it's basically studying sort of the details of how galaxies affect their surroundings. And then also we'll be able to do some sort of similar work that Hubble has done, for example, in honing in on those parameters of dark energy by studying the distances to galaxies precisely. So it's all about precision. And with WFIRST, for these particular studies, it's all about volume. So you need lots and lots of galaxies to be able to hone in on some of these problems. And that's why we're building WFIRST the way we are. It has this huge area, huge field of view.
Thank you.
Mm-hmm.
Let's take another in-theater question.
I'm not sure what my question is. So you mentioned earlier about looking through a straw and you would see 10,000 galaxies through the straw. How do you map the 5% of the universe that we can see? Who's the cartographer who's mapping what we can see? Do you have a space compass that you use that you move 2 degrees at a time. It's such a big challenge. I don't know how you map the universe.
Yeah, that's a great question. And so how do you map the universe? There's, the sort of pencil beam surveys I talked about, the looking through a straw, that is more to look deep into space. So we can actually map the cartography of the universe, if you will, more efficiently with large area surveys. So for example, the Sloan Digital Sky Survey on the ground, the Sloan telescopes, have been able to sort of map where the galaxies are. And this is how we found out about things like large-scale structures. The galaxies aren't random, that if you look at millions of galaxies, that you see that they form this cosmic web. And so that is a lot of the job of a lot of ground-based telescopes, and WFIRST would also have a part in that as well. Mm-hmm.
I'm going to go online again. I think I have 2 that are similar. So the one question is, why isn't the mirror in a protective housing like the Hubble was? And I think ties to this question, what happens if something hits the telescope, and how would you prevent it from happening?
Yeah, okay. So I'll answer the second one first. We can't prevent things from hitting the telescope. So we have a fairly good idea about that part of space, the L2 part of space, because we have spacecraft out there. We have a fairly good sense of what the micrometeorite environment is out there. So we know we'll get hit by little micrometeoroids. So they'll come along, they'll poke us, poke a hole through the sunshield, no big deal. We'll get little pocks on the mirrors, no big deal. So we expect for it to happen, and we don't expect that it will be a problem. Now, if something like boulder size comes along and smacks us, we're in big trouble. That's a bad day. But statistically, that's really, really unlikely. We don't expect that to happen. So we expect to get hit by little pieces of space dust, and it won't be a big deal. And then the first question was, why doesn't Webb have a mirror? Basically, why does Webb look weird, right? So when you think of a telescope, you think of a mirror with a tube around it, right? That's what backyard telescopes look like. That's what the Hubble telescope looks like. It's literally a mirror with a big tube. And the reason for that, of course, is to protect the mirrors, the detectors, whatever you have, from ambient light, from outside light. Webb is different because it's an infrared telescope, and so what we really need to protect the mirrors and instruments from is infrared light. And your big infrared source in that part of space is the sun, which is why we have the sun shield. So in effect, you can sort of think of the sun shield like the tube of a telescope, except it's just formatted in a different way.
Very good. In theater.
Can you tell me how big the package is that's actually going on the spacecraft, on the launch vehicle, mm-hmm. how much the package weighs, and how much did the entire telescope cost?
Sure. So, so the easy ones first. The whole telescope, top to bottom, is sort of 3.5 stories tall. So you could sort of get a sense from the full-scale model picture that I showed you, and from end to end on the sun shield, about the size of a tennis court. So that's the size, and that's of course why it has to be folded up so small. The inside of the rocket fairing that we're fitting in is about 5 meters, so it has to be all packed up to be no wider than about 5 meters. Mass. I don't know the mass. I should probably be able to rattle that off, but I don't know that off the top of my head. It's scientist to me, I'm not an engineer. But I do know this, fun fact, is that Webb is about half the mass of Hubble. So it's this big, huge, enormous thing, but it's relatively sort of fragile, lightweight. And of course, that's because we're going into space. We need to make things as lightweight as we can. And also because there's a weight limit for the rocket. If you make the telescope as lightweight as it can be, then you can use your extra mass margin to pack in fuel. And so the more fuel we have, the longer we can operate the telescope. So the life limiting factor for the telescope is propellant. Out in that part of space in L2, we sort of have a big lazy orbit around that theoretical L2 point. And so it takes rocket fuel to sort of keep it in that orbit a little bit. Cost. So the telescope cost to launch is $8 billion, billion with a B, and so that's the last couple of decades of work. So that's from the beginning up through launch. That's a lot, relatively speaking. That's a lot for a NASA mission. This is one of NASA's strategic big missions. Again, all most of the other telescopes I showed you on that chart are much, much smaller and focused. So that's why they only come around as often as they do, not quite so often. We launch these other smaller telescopes into space, every several years, whatever. But in the end, it will be less expensive than Hubble. The Hubble, especially if you count the servicing missions, will in the end have been more expensive. And so the subtext, the sub-question there, of course, is the obvious one: is it worth it? And I think that's something that we as a society have to decide, right? These are taxpayer dollars. This is a government-funded telescope. And so we as a society have to decide if we want to invest in that. And I think for NASA, when this question comes up, over and over, the public has been enthusiastically behind these endeavors. And in fact, if you poll the public and ask them what they think the NASA budget is, they way overestimate it, about 20 times, 40 times. And so the question of is it worth it is an important one that we have to discuss as a society. Of course, I think it's worth it because I'm a scientist. But I think that if you ask these deep questions, that I think society tells us that it's worth it too.
I'm going to jump back to an online question before going up to the microphone. The question is, will the James Webb be able to confirm the idea that black holes are critical to galaxy formation?
Ooh, that's a great question. So I think, yes, I think that Webb will absolutely make large strides on the whole area of how galaxies and black holes evolve over time, and of how black holes interact with their galaxies and vice versa. So we know that black holes are common. These supermassive black holes with, billions of times the mass of the sun exist inside every galaxy that we know of, every nearby galaxy. How they got that big is a big mystery. No idea. We think this galaxy merging process is a really important part of that process, that maybe the black holes merge. Or who knows, maybe the galaxies collide together and the black holes get kicked out. There's a lot that we don't know about that process. But again, that's one of the reasons we build these big telescopes, is to help us learn more about that process. But I think absolutely Webb will help us learn more about the whole process of how black holes form over time, how they interact with their galaxies, and how the galaxies influence the black holes.
Let's go in theater.
The question is about sequence of time. You mentioned that the intention is to look deeper in the universe in order to see back in time. The question: how do you know that further is further in time? We know that it takes time for light to travel. Right. We know that universe expands. We know that there are all kinds of processes of forming stars. So is it necessarily true that further is further in time?
So this whole idea of looking further in distance, the idea that translates to looking back further in time, really does rely on the assumption that light has a finite travel speed, and that we can sort of map it back, right? And so the process of how we use the light from galaxies to figure out the distances comes through mostly spectroscopy. So we take spectra, the signature or the chemical fingerprints of galaxies, and we look for specific emission lines. And we say, there's a hydrogen line. I know if I look at hydrogen here on Earth, this is the wavelength where it happens. And so if we look at a galaxy and we say, that line's been shifted to the red part of the spectrum, we can calculate then how far away that galaxy is. So that's the process by which we determine the redshifts and the distances of galaxies. But it does fundamentally rely on this fact that light has a finite travel speed.
I think there's one more question here in the theater. Perfect.
I've got two questions. One's easy. Who's James Webb? And
okay.
the second question is, I've been to a couple lectures where they talk about the universe. I'd like to hear what you think, what is beyond that universe. Is it finite, or do you think it goes forever?
Okay.
So like I said, first question's easy. Second question, not so much. So the first, James Webb was the leader of NASA, the NASA administrator during the development of the Apollo program. So he was largely responsible for the conversations with JFK, with Kennedy, that eventually got humans to the moon in Apollo. But in addition to that, he did something very instrumental that changed the purpose of NASA in the very, very early days of NASA. He said that in addition to launching rockets to space, launching people to space, that NASA should be doing science. So James Webb really instilled the value of science in NASA early on. And so that was the reason this telescope was named after him. Second question. Wow, yeah, that one's a lot harder. So you ask if, what's beyond the visible universe, basically. So as a strict observationalist, I will say we can't observe it, so we don't know. But going beyond that, we don't know. I'm really interested, and I've talked to a couple of people here today about the prospect of what lies beyond our observable universe, about the prospect of multiple universes, the multiverse, about the idea that, we could live in sort of a bouncing universe. Now we know that the universe is not only expanding, but that it's accelerating in its expansion. So that's what dark energy is. We don't know why, so we call it dark energy. So we don't expect that, since it's accelerating, that it would stop and slow down and come back and bounce. But there could be scenarios in which it's instead of bouncing sort of back and forth like that, what's the right word? It's not bounce, but basically that other universes could sort of be born. It's, multiverse is not my area of expertise, but it's super interesting. And so I think that's one of the cool things about this place, actually, is all these sort of big questions about theoretical physics and about string theory and about the multiverse. It's really fun stuff. But for now, I'm interested in what Webb's going to see. And we'll be able to see back to the early universe, which is going to, I believe, reveal really a lot about the whole evolution of our universe. I mean, we're missing the first step, right? We've done all this study of all these galaxies looking back to the most distant ones we can, but we're really missing the first piece of the puzzle and how the galaxies got started. And so I think that's going to be one of the really cool things that Webb does is to help us learn more about that very first epoch of galaxy formation.
Ladies and gentlemen, Dr. Amber Straughn.
Hi all, and welcome to the first guide for the month for the year of 2022, and this being for January 2022 and early February. Even though this presentation is coming to you via YouTube, I'd just like to remind all members that the Briars Astronomical Centre is open to members, subject to appropriate COVID precautions. So looking at the highlights for January-February 2022, you can see that there's a considerable amount of comet activity. There'll be more about the comets later in the presentation, but enough suffice to say that a significant number of these comets are evening objects, and so certainly objects that most people can have a look for. We have our full moon on the 18th of the 1st, so just past, and on the 23rd of the 1st, Mercury is in inferior conjunction, which for the newer members means Mercury is between the Earth and the Sun. So not a really good position for us to have a look at. First to the second, we have a new moon, so a good opportunity to get out there and look for those comets, and also the Alpha Centauri's meteor shower, which occurs between the 28th of the 1st and the 21st of the 2nd, with its peak on the 8th of the 2nd, and I'll speak a little bit more about that later. We have a first quarter moon on the 8th of the 2nd, and back to a full moon on the 17th. Looking at the sky for January, looking to the south, in particular note, you'll notice the large Magellanic Cloud with the Tarantula Nebula is fairly prominent, as is the star Canopus, and a little bit further down, the Eta Carina Nebula. Something to take note of here, particularly for those who want to go comet hunting at some stage, is the position there of Pisces and Cetus over on the western horizon. Looking at the January night sky looking to the north, very much a summer sky with Orion very prominent in the middle there. The advantage of that is Orion is an extremely easy constellation for people to identify, and you can generally work or star crawl from there to other major stars such as Sirius and Canopus. And Orion itself contains some quite interesting deep sky objects for people to look at too. Obvious one being M42 there, the Orion Nebula in the Sword. But there's a couple of other interesting ones there too. You've got the Horsehead Nebula and the Flame Nebula, and both of those are right adjacent to, as we look at it, the right-hand star in Orion's belt. Now these are difficult objects to see with the naked eye through a telescope, but they're certainly interesting objects for people to have a go at with their photo equipment. Looking further afield, you've got the Ghost of Jupiter up there to the right. That's a planetary nebula. Looks a little bit like Jupiter, but a little bit fainter because it's actually a big gas cloud rather than a solid planet. And a few other things there, such as the Hyades and the Pleiades. Looking at the planet show for this month, it's not all that spectacular. In particular, Mercury was at maximum elongation early in January, but it has subsequently moved into inferior conjunction, positioning it between Earth and the Sun. So not in an ideal place to view, and the next time it becomes visible it pops up in the early morning sky, so one for the early risers. Venus has already passed through its inferior conjunction, same boat as Mercury between Earth and the Sun, and it should reappear in the early morning sky towards the end of January. Interesting note with Earth, we always may wonder why the southern hemisphere summer seems to be a lot worse than it is for the north, and that's because at this time of the year Earth reaches perihelion, or its closest approach to the Sun. So we're only 0.98 astronomical units away, and under the inverse square law we're obviously getting a little bit more heat than we would otherwise. Looking at the outer planets, Mars is a morning object visible in the eastern dawn sky in Ophiuchus, slowly moving into Sagittarius as the month progresses. Still a fair way away, so not a lot of detail to be seen, but as the year progresses it will move towards opposition later this year. Jupiter and Saturn, I'll group these two together because they're still relatively close to each other. Jupiter can still be seen low in the western evening sky. Won't be long before it disappears into evening twilight as it heads towards its conjunction. Saturn is a little bit closer to its conjunction than Jupiter, and as such is very much in evening twilight at the moment, and so not or is rather difficult to even see visually. Around late February it will return to the early morning sky. Uranus is still in Aries, will be there until I think 2024, and can be found in the northwestern evening sky. It's very close to the 6th magnitude star 29 Arietis, which is a posh way of saying Aries, and they're both about the same magnitude. The way you can pick which one is Uranus as opposed to the star is look for its slightly greenish disk. Neptune in Aquarius, still a challenge to get without a go-to scope, but not impossible. It really only appears in most of our scopes as a blue dot, and even if it was a little bit bigger, there's not a great deal of detail to be seen on it. Looking at the appearance of the planets for the month of January, Mars and Venus in particular don't look all that spectacular because we're essentially looking at the unlit rear of them as they pass through inferior conjunction. Venus on the 9th of January and Mercury inferior conjunction on the 23rd. However, Venus being fairly close to it is still a reasonably bright object. And will appear as a very thin crescent. Mars, as I said, is still a fair way away. It is a morning object and will slowly get brighter as the year drags on. So you can certainly find it now, but don't expect to see too much detail. Saturn, pretty much as it appears with its rings tilted towards us there, it is very much in evening twilight now, and so it can be very difficult to spot with the naked eye. You may still be lucky with a telescope. Jupiter a little bit higher. It's also heading into evening twilight, so won't be long, probably towards the end of the month we'll lose visual sighting of Jupiter as well. Once they go through their conjunctions, they will both return to being morning objects, just a little bit further apart than they were this year. And Uranus and Neptune, as previously stated, not a lot of detail on either of them. The main thing you're looking for both of those is in particular their colour. Okay, looking at the other stuff that's out there for us to have a squiz at this month, we're looking at Comet Leonard once again. Most people would be aware that Comet Leonard has been rather prominent over the last month or so. It's still in the evening western sky, just to the left of and about the same elevation as Jupiter. As this planet and the comet move into eastern twilight, or the evening twilight, sorry, it may be a little bit harder to find. It is also expected to fade from 6th magnitude to 9th magnitude, so it's only going to contribute to the difficulties. Comet Borrelly will remain around about 8th magnitude and visible until late in the evening in Cetus, moving into Pisces at the end of the month. And this is why I highlighted where Cetus and Pisces was back on the star charts. Both there on the near to the ecliptic plane on the western horizon. So if you have a look in that area, you have a reasonable chance of finding Comet Borrelly. In addition to that, Comet Cowell 2 is visible until just before midnight at around about 10th magnitude. and it can also be found in Cetus along its border with Pisces. So you've got the two comets in that very close proximity of the sky. Hopefully you can find one or the other or both. Comet Churyumov-Gerasimenko, moving through northern Cancer around about 10th magnitude. Of all the comets available, it is the one that's best viewed by the night owls after midnight. And last of all, Comet Atlas, also visible for most of the night in Gemini at around 10th magnitude. It is near Alpha Gemini, also known as Castor, which are quite easy to spot due to its relative proximity to Pollux. It'll drift south over the next few months, meaning essentially that it'll move higher into the night sky. So Comet Atlas, if it gets a little bit brighter, might be one to keep an eye out for. And last of all, we have a meteor shower this month, known as the Alpha Centaurans. They're active from the 28th of the 1st until the 21st of the 2nd, peaking around about the 8th of February. Known for bright yellow and blue fireballs, occasional really blue one. They should be reasonably easy to find coming from the Alpha Centauri area, and at anywhere from around about 8 to 10 per hour. So if you want to go meteor spotting, you're a reasonable chance to spot one of these Alpha Centaurans. And that concludes Sky for the month tonight. Once again, hoping that next month it'll be face-to-face. The information provided tonight was provided by Astronomy 2022 by Wallace Dawson Northfield. I believe the Society has a few of those in our merchandise area, so have a chat to Simon or some of the other people manning that area, and hopefully be able to grab yourself one of those books. They've got a lot more information than what I've given here. Once again, thank you for listening, and hope to see you all next month.
I don't think it is very useful to speculate on what God might or might not be able to do. Rather, we should examine what He actually does with the universe we live in. All our observations suggest that it operates according to well-defined laws. These laws may have been ordained by God, but it seems that He does not intervene in the universe to break the laws, at least, not once He had set the universe going.
In the cauldron of the early universe, no light could escape the dense, opaque fog of primordial gas. As this cosmic soup of atomic particles began to cool down, hydrogen atoms began to form, leading to the universe's first bright, violent new stars, burning through the fog that once blocked all light from escaping the expanding universe. Some of these early photons have traveled unhindered through the vast, empty expanse of space for 13.5 billion years, and will reach their final destination here on the man-made detectors of the James Webb Telescope. A space odyssey coming to an end because of the curiosity of humans. The James Webb Telescope is going to give us our first detailed glimpse of this early universe from which we and everything we know was born. The James Webb Telescope is a $10 billion endeavor, an endeavor that has eaten into NASA's limited budget, consuming 1/4 of NASA's entire astronomy budget for years. And in the early hours of a tenuous launch date of December 24th, this $10 billion gamble will launch aboard the Ariane 5 rocket, a European heavy lift launch vehicle from the European spaceport in Kourou, French Guiana. Astronomers, physicists, and enthusiasts alike We'll look on with nervous excitement as this rocket carries the next generation in human curiosity. This is the insane engineering of the James Webb Space Telescope. The combination of technologies required to make the James Webb Telescope possible are unique to this time period in human history. The launch vehicle, the image processing, the electromechanical systems, the cooling systems, the mirror, and the sun shield. This endeavor is the culmination of not just decades of work from the engineers and scientists at NASA, but thousands of years of work of our ancestors. The materials and engineering required to peer back 13.5 billion years into the reionization epoch are a punctuation point in human history that we, the human race, should be celebrating and watching with bated breath together. The launch will take place here in French Guiana, a spaceport ideally located on the Earth's equator to give the James Webb Telescope an extra push towards its final destination. The James Webb Telescope will not be in orbit around Earth like Hubble. It will be launching to a destination 1.5 million kilometers from Earth, Lagrange Point 2. Lagrange points are special points in space where small objects like satellites can stay more or less in the same position relative to the gravitational bodies that they are traveling with. This happens because the gravitational pull from the two bodies precisely equals the centripetal force required for the object to move with the gravitational bodies, like little parking spots in space that allow satellites to sit in a relatively stable position while using a minimal amount of fuel to stay there. There are 5 Lagrange points between the Sun and Earth. L1 lies between the Sun and Earth. It's extremely useful for Sun observation satellites. However, the nature of the James Webb Telescope's job wants it to avoid the light from the Sun as much as possible, because it is an infrared telescope. Infrared is heat, and the heat emanating from the Sun would completely saturate its sensors and make observing the cold, distant past impossible. So, it will be launching to L2, located about here. Here the telescope can turn its back to the Sun, Earth, and Moon, which will stay in the same position, nicely lined up behind the telescope, thanks to Lagrange Point 2's unique physics. In order to operate correctly, the dark side of the telescope needs to operate at minus 233 degrees Celsius. Without a way to block out the heat from the Sun and Earth, the telescope would be scorched at 83 degrees Celsius, nearly hot enough to boil water. This is a huge amount of heat to block, and to do this, the James Webb Telescope will carry a massive shield on its back like a tortoise.
And making such a device is a very, very tough problem.
That's Mike Mansell, Mission Systems Engineer for the James Webb Telescope.
We had to map every heat flow to make sure that we do not let any heat leak through from the hot side to the cold side. To make sure that that sunlight, which is dumping approximately 200,000 watts of power in our direction, we only want less than about a watt of that to make it through to the telescope so that it passively cools down to those temperatures.
Preventing that heat transfer is, as Mike said, a very tough job. Heat can transfer in 3 ways. Conduction, where heat is transferred from atom to atom in direct contact with each other, like heat traveling down a copper pipe. Convection, where heat is transferred from the physical movement of atoms. And radiation, where heat is transferred by electromagnetic waves. In the vacuum of space, convection isn't a concern, so that leaves conduction and radiation as methods of heat transfer. Let's see how the James Webb Telescope is managing these. First, material choice. The sun shield needs to be light, strong, resistant to degradation from solar radiation, dimensionally stable across a range of temperatures, and reflective. That's a long shopping list of requirements, and Captain, a type of high-performance plastic, manages to check all the boxes. Each layer of the Captain's sunshield is incredibly thin. Layer 1, the layer closest to the Sun, is the thickest at 0.05 millimeters, while the next 4 layers are just 0.025 millimeters thick. Captain by itself is actually transparent, which isn't a fantastic trait for a sun-blocking heat shield. Thankfully, the wonder material that is Captain can be easily coated in other materials. Each layer is coated in a 100 nanometer thick coating of aluminium, giving the sunshield its reflective appearance. This reflective quality helps prevent heat transfer through radiation by simply bouncing that radiation back to space. And with the gaps between each layer, the heat that is absorbed can't easily transfer through conduction or convection, taking advantage of the highly insulating vacuum of space between each layer. Heat could still transfer between each layer through radiation. The outermost layer will gain heat and start glowing with infrared radiation, just as we see through an infrared camera. In order to prevent this, the sunshield has some clever engineering designs. The layers are angled relative to each other to ensure the reflected radiation between each layer is funneled outwards to space, ensuring that each layer gradually reduces the temperature as it gets closer to the critical components in the instrument bay. The layers gradually get smaller in area from layer 1 through 5, ensuring the mirror only has a direct line of sight with the coldest layer at all times. Layer 1 itself is also coated in a special silicon coating 50 nanometers thick, giving it this pink appearance. Silicon was used because it has high emissivity, simply meaning it emits a lot of energy it absorbs out as thermal radiation, meaning the material will not hold onto its heat, which would give it time to conduct through the structure of the spacecraft to areas we want cool. This high emissivity silicon coating is applied to layer 1 and 2, the 2 hottest layers, helping them send their heat back out to space, away from the spacecraft, as fast as possible. These design choices are what allow the heat shield to maintain the massive heat differential between the hot and cold side, but blocking heat is just one challenge.
That's one of the bigger challenges, along with just designing a deployment system that does this complicated, and necessary unfolding reliably and correctly.
In order to fit inside the fairing of the Ariane 5 rocket, the sunshield has to be folded and stowed before launch, leading to some incredibly complicated mechanics to ensure it unfolds correctly when game time arrives.
Deploying things in space is always difficult, but when you're deploying rigid structure, that's generally what us engineers would call deterministic. That's relatively easy. Membranes and cables are almost inherently non-deterministic. And if you want to, describe or illustrate what that means, try pushing on a string. The string will move, but if I ask you to determine the shape that it will assume, you will have a very, very hard time doing that. So to control these almost non-deterministic things takes a great deal of effort, a great deal of trial and error. And even after we're done getting it, getting the design right, the one thing about the sunshield, it's almost like a parachute, or it's very similar to a parachute. The parachute will work, but it's also only as good as the very, very last time you fold it. And you're going to find out whether you folded it correctly or not when you use it.
The unfolding process will begin a few days after launch, not too far from Earth, starting with relatively simple mechanisms, with the solar panels and communications antenna deploying. The truly nerve-wracking process begins on day 7, as the spacecraft is coasting towards L2. There are over 300 single points of failure in this unfolding sequence, 300 chances for a $10 billion, 25-year project to end. 107 pins holding the sunshield together have to be released on cue to allow the system of pulleys, motors, cables, bearings, and springs to begin unfurling the sunshield into its precise, complete shape. This process will take 3 days, and once complete, the optical components will unfold and lock into place, completing the transformation process, but we are most certainly not in the clear. The likelihood of the tennis court-sized sunshield being struck by micrometeorites is fairly high, and because this is a thin layer of plastic stretched out under tension, a small tear caused by an impact could cause a runaway tear ripping through the whole sunshield. To prevent this, ripstop seams have been molded into the sunshield, which will arrest tears and keep them confined to a single portion of the shield without compromising structural integrity. The film has also been carefully molded with corrugations and other shapes to stiffen and shape the shield as needed. This passive cooling system helps tremendously, ensuring the dark side of the telescope is shielded from the sun's heat, keeping its sensitive heat detecting instruments at 40 degrees Kelvin, about minus 233 degrees Celsius. But parts of the telescope, specifically the mid-infrared detection instrument located here, needs to be even colder to work correctly. It needs to be 7 degrees Kelvin, just 7 degrees off the absolute minimum temperature of the universe of 0 degrees Kelvin, and for this we need active cooling. The James Webb Telescope includes an innovative cryocooler for this purpose. The challenge in developing this cryocooler alone was immense, costing $150 million. Getting cold temperatures is just one small part of the design. Vibration has to be eliminated, as the tiniest movement of the telescope could cause massive blurs in the image as it attempts to focus on objects billions of light years away. That means eliminating moving parts where possible, and when that can't be done, incredibly precise machining and movement is needed to balance weights as they move. The cooler also needs to use a tiny amount of electricity, as the telescope only has 2000 watts of power provided by its solar array, and it needs to run reliably for years. That means a closed-loop cycle, with our refrigerant being continually reused. I found this explanation of the cryocooler on NASA's site. The pre-cooler features a 2-cylinder, horizontally opposed pump and cools helium gas using pulse tubes, which exchange heat with the regenerator acoustically. Okay, horizontally opposed pumps with carefully balanced pistons that will cut vibration as the weights balance each other out. But the rest of that explanation sounds like it came straight out of a sci-fi novel. A sound wave is just a pressure wave, and pressure and temperature are directly proportional. Higher pressure will cause higher temperature. One way we can take advantage of this is by creating a standing wave, where the peaks and troughs of the wave are stationary. We can do this in a closed tube, where the resonant frequency of the tube is determined by the tube's length. Here, the sound wave will bounce off the closed end and create a region of compression and high pressure, and therefore high temperature. This alone isn't terribly useful. The energy and temperature in this system will stay relatively stable, left on its own. But what if we could extract some of this heat with each cycle? Then, on each cycle, we could gradually cool the overall system. To do this, we need a way to pass energy out of the system. This is done with a stack, a porous material with air gaps that allow sound to pass through it, which is placed so that it smoothly spans both the hot region at the end of the tube and the cold region in the center, like this. A heat exchanger is then placed on either end of the stack, one for the hot side and one for the cold. The hot heat exchange will conduct its heat to the center of the sunshield, where it can radiate out to space, while the cold portion will conduct its heat, or lack thereof, to a copper plate attached to the back of the infrared sensors to cool them to 6.2 degrees Kelvin. This is obviously an extreme oversimplification of the actual operation of the pulse tube cryocooler. This is just a basic explanation of the physical phenomenon that allows it to work. The pulse tube cryocooler is quite possibly the most fascinating part of this spacecraft to me, utilizing a simple physical phenomenon with extreme precision, allowing those infrared sensors located in the center of the telescope's beautiful golden mirror to work. The golden mirrors are the most striking part of the telescope, made of 18 hexagonal segments, 6.5 meters in diameter. So, what's the deal with the design? It's unlike any telescope mirror I have ever seen. The mirror surface itself is beryllium plated in gold. That's a unique and expensive material choice. We need the structure of these mirrors to remain in an extremely precise shape to reflect light as desired. They can't bend and they can't warp with temperature changes, and they also need to be extremely lightweight to reduce launch costs. Beryllium is a lightweight metal. With an atomic weight of just 4, it's much lighter than silica glass, a more traditional mirror subsurface material, while being far more capable in dealing with the cryogenic temperatures the mirror will operate in, keeping its shape and not contracting so much that it ruins the carefully shaped curves of the mirror. While nowhere near as strong as steel, beryllium is much stiffer with a Young's modulus of 300 gigapascals. This means that while beryllium is easier to break than steel, it's harder to deform before it actually breaks, giving it excellent dimensional stability. On a pound-for-pound basis, beryllium is 6 times stiffer than steel, making it the perfect subsurface material for this mirror. However, it is not reflective, and for that, we need to turn to gold. Gold is not the best reflector of visible light, being particularly poor at reflecting the lower frequencies of the visible spectrum, giving it its distinctive golden hue. But, critically, it is an excellent reflector of the infrared spectrum, while being very unreactive, ensuring the mirror surface will not tarnish and lose its shine during its operation. To reflect that light, a very thin coat, just 0.1 micron in thickness, is coated over the polished beryllium subsurface, taking just 48.2 grams of gold, about the same weight as a golf ball. A surprisingly small amount for the huge mirror, which has a collecting area about 25 meters squared, 5.5 times larger than Hubble's 4.5 meters squared circular glass mirror. The mirror needs to be massive, and to explain why, I asked Mike Mansell.
Well, I could tell you how much it's collecting. First, we're looking for stars or stellar objects or things that are approximately going to be a nanojansky. And to explain what a nanojansky is, a unit of brightness. It's very, very dim. We're looking for among the dimmest things there are in the sky. If I was to put a child's nightlight, puts out about 5 watts, put it on the surface of the moon and look at it from the Earth, that source would appear to be 20 nanojanskys. So we're looking for objects that are 1/20th as bright as that. To do that, you need a big telescope. Picture light as rain coming in. If you want to collect a lot of rain, you make a big, wide bucket. Well, even at the size of our bucket, 6 meters across, we're only collecting about 1 photon per second, 1 particle of light per second. And to put that in perspective, I'll go out tonight or any night and look at the brightest star there is in the sky. Your eye is probably collecting about 1 million photons per second from that star. So to see these very dim things, the dimmest things there are to see in the universe, you need a light bucket that's at least 6 meters in diameter.
1 photon per second really puts things into perspective. Mike and the rest of the team working on the James Webb Telescope actually wanted the mirror to be bigger, but the cost of launching a mirror that size, between the increase in weight and limited space available inside the Ariane 5 fairing, was not cost effective. They maximized the size with the resources available, and incredibly, even though the mirror's collecting surface is 5.5 times larger than Hubble's, the James Webb mirror is 62% lighter than Hubble's massive solid glass mirror. That is an astounding weight saving, driven by launch weight requirements to get the telescope to L2. And the mirror is even programmable. When Hubble first began transmitting images back to Earth, it became clear that there was something wrong with the telescope's optics. Instead of the crisp, awe-inspiring images we are all familiar with today, the early images came back blurred. The mirror had been ground down to flat by a mere 2,000 nanometers, 1/50th the thickness of a human hair. But that was enough to cause the light to be focused incorrectly on the telescope sensors. Replacing the mirror was not an option, but Hubble was designed to be serviced throughout its lifetime, featuring modular equipment bays that allowed older equipment to be removed and replaced. In order to correct the issue, corrective optics were installed into one of these equipment bays, like a giant pair of glasses for the $1.5 billion telescope. James Webb will not be serviceable. It's simply too far away from Earth, beyond the range of any space vehicles capable of carrying humans to service it. If there was a problem with the mirrors, that would be game over. But the engineers were not taking chances this time, and have engineered a system capable of adjusting its focus by itself. Each of the 18 separate mirrors can contort its shape and adjust its position relative to the secondary mirror located in the main mirror's focal point. The weight-saving isogrid rear side of the beryllium mirrors are assembled with a system of backplates, struts, and motors that can not only adjust the mirror's rotation, but with the center motor and these struts, the mirrors can actually change their curvature to adjust the focal point of the mirrors, a feature that could have corrected Hubble's issues from Earth. Once fully deployed, the telescope will begin its calibration phase, with each mirror adjusting itself until each of the 18 segments have aligned correctly with the secondary mirror, a 0.74 meter convex mirror, which itself has 6 motors to adjust its position. These motors and control systems are so precise that the mirrors can adjust their positions in steps on the scale of wavelengths of light, creeping closer to alignment by increments of 1/10,000th the size of a human hair. That is an astoundingly accurate electromechanical system. The engineers of the James Webb Telescope performed this calibration test here on Earth with an absolutely massive vacuum chamber that can be cooled down to the same temperature that the telescope will operate at, ensuring proper focus can be achieved. But the job to get a clear image isn't done with primary and secondary mirror alignment alone. They focus the light onto the Cassegrain focus, which is located inside the aft optics subsystem. This black protrusion in the middle of the primary mirror, which blocks stray light from entering the aperture. In the darkness within, there are 2 more mirrors, one of them being the fine steering mirror, and this thing is the world's most expensive image stabilization tool. It is controlled by the fine guiding system. The fine guiding system is locked onto a guide star, and its job is to keep that star in the center of its field of view. Every 64 milliseconds, the fine guiding system will send signals to the attitude control system to make adjustments to ensure the telescope stays on target. This attitude control is done with a combination of 6 reaction wheels located inside the spacecraft bus, below the heat shield, and with the fine steering mirror. This mirror will constantly be adjusting itself to ensure the target of the telescope stays steady on the sensors, minimizing blur. The telescope also has thrusters for larger position maintenance. 191 litres of hydrazine and 95.5 litres of its oxidizer, dinitrogen tetroxide, will be stored inside the spacecraft bus that will feed 20 different rocket thrusters scattered around the telescope. There are 8 thruster modules, 2 on each corner of the spacecraft bus, to aid the reaction wheels in spinning the telescope to point towards points of interest. These 16 engines will be fed with hydrazine only, a monopropellant reaction where the hydrazine is passed over a catalyst, causing a highly exothermic reaction, breaking the hydrazine down into nitrogen, hydrogen, and ammonia. The other 4 motors are for orbital and positional control and require more power. They will be fed by both hydrazine and dinitrogen tetroxide. This fuel and oxidizer mixture react hypergolically to form nitrogen and water. Hypergolic meaning they do not need an igniter, They simply ignite on contact with each other. Hydrazine is an excellent choice for a long-lasting mission like this. The hypergolic reaction means the motors can repeatedly and reliably fire without a point of failure causing issues, like an igniter breaking. Hydrazine is also stable for long periods at room temperature, allowing it to be stored over the expected 10-year life cycle of the James Webb Telescope. Unfortunately, that life cycle is limited to 10 years precisely because of the fuel. Between pointing and orbital maintenance, we will run out of fuel at some point, and NASA currently has no way of refueling the telescope. But rumors are, behind the scenes, NASA is looking to develop the technologies required to refuel the James Webb Telescope before its demise 10 years from now. Robots capable of refueling spacecraft far from Earth is an exciting concept. The James Webb Telescope could end up teaching us many more fascinating things beyond the early stages of the universe.
It's my hope as an engineer, and after being 25 years on this job, that eventually our telescopes, the really, really, really big ones of the future, will be built in space. Testing James Webb, a telescope that's designed to work in space, has been a very difficult thing to do on the ground. And I'm hoping that someday we'll be building these things in space, testing them in space, tweaking them in space, and then deploying them in space that way.
We are on the frontier of a new space age, and the James Webb Telescope is a milestone on our journey towards being a more capable spacefaring society. This is just one of many milestones in our brief time as a species capable of escaping our planet's gravity. From building our incredible global positioning network and sending satellites to the far reaches of our solar system, to visiting the moon and building reusable rockets. It's never been more exciting to be an aerospace enthusiast.
Now this is perhaps one of the most beautiful kind of features that volcanoes can make, a very big, high eruption column. And in the last 10 years or so, we've made really a lot of progress in understanding what these explosions do and the kind of things that can go on. And for most of the rest of this lecture, I'm going to be talking to you about the kind of things that go on in these big explosions. Why are they a problem? Because this stuff coming out of the volcano is coming out as a very fast stream of hot gas and dust and magma and bits of liquid and all sorts of stuff. It's coming out at a few hundred meters per second. That's about the speed of a jet airliner. That's how fast it's coming out. But if I was just to throw something into the air at the speed of a jet airliner, it would go about 1 or 2 kilometers into the air, and then it would fall down. Now, these things go 20 or 30 kilometers into the air. They go much, much higher than they should. We're going to do an experiment now, which is going to help us to understand what actually goes on. This is a tank of water, but rather special water. At the top of the tank here is fresh water, and at the bottom of the tank is salt water, which is much heavier, it's denser than the fresh water, and there's a gradient between the two. This is to match the atmosphere, and the atmosphere, the air, is much lighter at the top than down the bottom where we are here, where it's denser. At the bottom of my tank I have a volcano, and I'm going to feed a stream of liquid into that volcano, which is coloured red. And the liquid that's coming into the volcano is fresh water. It's the same density as the top of the tank, and it's a lot lighter than everything else in the tank. So you'd think that, yes, of course, this stream will rise up to the surface where it's got the same density as the surface water. Well, let's see what actually happens when we do it. So I'm going to open the tap here. Let's see what happens. Here it comes. And it's coming up, and it's not getting up to the top. It's going up about halfway, and then it's spreading out sideways. It's making a mushroom cloud. And this mushroom cloud is growing more and more sideways. It's not going up. Now that's surprising. How can that be if the liquid which is coming out is the same density as the surface of the tank, and it's much lighter than the density in the middle of the tank? what's actually happening in this demonstration is that as this stream of liquid is coming out from the volcano, it's sucking in water from round about. And of course, the water round about is denser than the stream of liquid coming out of the bottom of the volcano. And so that makes the stream as a whole denser, and it can't rise up as high as we expected at first. It can only get halfway because it's got denser by sucking in all this liquid round the side. And this process of fast jets sucking in whatever is surrounding them is actually very common. It happens all over the place. And this rather lovely demonstration, which produces these big mushroom clouds, is going to help us understand what happens at Mount St. Helens. Thank you very much. Now, this big cloud here, this big eruption column at the top also made a mushroom cloud. And the next picture will show what that mushroom cloud looks like from a distance. Mount St. Helens is buried in the middle of the foot of that cloud. And this thing is so big that it couldn't actually fit in a camera frame. And so this is a picture made up of lots of pictures which have been glued together to make this one. And this mushroom cloud rose up to a height of about 20 kilometers before it spread out sideways. Now, what's happening in this is that the hot stream of gas and rocks and magma coming out of that volcano is again sucking in the surrounding air, but the air, of course, is light. And the air is then heated by that hot stuff coming out of the volcano. So the air which is sucked in expands. And this is like tying lots of hot air balloons onto what's coming out of the volcano. So it rises much higher than it would otherwise rise. So whereas that tank, the mushroom cloud, the stream went lower than we expected, here it went higher than we expected, the process is exactly the same, that both of these streams coming out of the volcano sucked in the surroundings, and that's what makes the effect. It so happens here that because the air which is sucked in is heated and expands, this goes up. In the tank, the liquid which was sucked in was actually heavy, which prevented it going higher. But the process is the same.